Good morning and welcome to a special Astraveo Coast-to-Coast episode talking about planetary alignments, which is going to happen. There's going to be one tomorrow morning and one at the end of June. Now, this is a somewhat special episode, as you can tell. I don't have my sidekick, Joseph, with me. He is busy in California doing other things. So we didn't want to miss the excitement of the heavens. So I said to him, okay, I'll do it myself. I'll jump in front of the green screen and put some images up. So unfortunately, I won't have his great humor, his great knowledge, and his sort of wonderful presentation skills. But I'm going to see if I can talk us through a little bit about planetary alignments and why we see them. Are they important? Do they affect our lives? And just some of the astronomy behind it, because it's sort of really exciting to see in the sky. So I'm going to show you some images first, because I think we should talk about what exactly a planetary alignment is and when there's the next one. So let me share my screen with you, please. There you go. So here is a depiction of the planetary alignment, which is going to happen very early tomorrow morning, about half an hour before sunrise. Now, this image I've taken from astronomy.com, so full credits to them. Thank you for having produced this wonderful graphic. Now, this is what we could see tomorrow morning, assuming it's not too cloudy and your view is not unobstructed. So it'd be before sunrise. Now, here the sunrise is extremely early on the East Coast right now where I am. But we'll be able to see this very, very thin crescent moon. We're about 2 or 3 days before new moon. I think new moon's on the 6th of June. So it's about 2 days before. So it'll be a very, very thin crescent. Now, as you can see, there are several of our solar system planets available to us in the night sky here, or the very early dawn sky. So we have Jupiter and Mercury right next to each other. We have Uranus in between Mercury and the Moon. Then we have, as we go through Aries and Pisces, the constellations, we hit Mars, the beautiful red planet, of course, the very faint Neptune, and then Saturn, which is up in Aquarius. Now, as you can see, 1, 2, 3 will include the moons that orbits us, 4, 5, 6. There's essentially 6 planets in a line there, plus the moon. Now, so what the planetary alignment looks like in the sky is our solar system neighbors appear to line up. Now, this can be a little bit deceptive here, because if you go out early tomorrow morning, about half an hour before sunrise, you're going to be contending with a few difficulties. First of all, you can already see in this graphic from astronomy.com, there is a little bit of early twilight dawn. You know, you're seeing some lights from the sun already starting to come up above the horizon because of scattering. We've also got this very faintly illuminated moon. That shouldn't be a problem for us. But then we have Uranus here and Neptune. Now, they are not visible to the naked eye, so you will only be able to see those with a good pair of binoculars or a slightly longer exposure photograph. Saturn should be very visible. That's easy. Mars is also almost always very, very good for the naked eye. Of course, it's very red. Jupiter and Mercury. Jupiter, of course, blazes away. We'll see Jupiter. Mercury might be difficult. I don't know the phase of Mercury right now. I could have looked that up, I suppose, but it's going to be, unless it's full on and it's this side of the sun, not the far side of the sun, it's going to be difficult to see. And so you might not get Mercury. It could be lost in the pre-dawn haze there of twilight. So really, you're only going to be able to get Jupiter if you can see very, very low down to the horizon. Obviously, you'll see the moon pretty well with the unaided eye, and then Mars and Saturn. Now, they're still in a more or less straight line, so that's still pretty cool. Now, a lot of people ask the question, why, who cares? Are planetary alignments important? Do they affect our lives? And the answer is no. I mean, they're sort of pretty to look at in the sky, and they prove a great astronomical point. They prove a really nice demonstration of the solar system dynamics and morphology. But do they per se affect us? No is the answer. And so they do take really nice pictures if you're really lucky to get it. Now, it depends on, like I said, if you've got an unobstructed view to the horizon off to the south east there, because the sun is in the southern hemisphere right now. It depends on whether you can, if there are any trees in the way, is there in early morning haze? There's all kinds of reasons why we might not get a great view. Now, with the moon being such a low phase, right, it's 2 days away from new moon, you could probably take a longer exposure photograph and Uranus and Neptune might come out. So I'm talking here by long exposure, I mean maybe 4 or 5 seconds. You don't want to go much past 10 seconds because then you start to get smearing And what that by smearing I mean is you're starting to see the orbital motion, I'm sorry, the rotation motion of Earth, the sidereal motion of the Earth turning on its axis. These planetary objects and the moon, they will appear to sort of smear. So it doesn't look quite as nice. But if you can do a 4 or 5 second exposure with a decent sized camera, I think you're in business. It'll look really, really good. Now this is on the 4th of June, so tomorrow for me. I'm in the 3rd. It's 3rd of June right now. But there is going to be another planetary alignment on the 30th of June. This is about 1 hour before sunrise. Now there's a lot more stars on this one, so it's a little bit more harder to interpret. Now again, this is from astronomy, our friends at astronomy.com. Again, we have Saturn, we have Mars. Now the moon is going to be near its last quarter, so it's going to be about half illuminated. Now, that could make it difficult to see Neptune and Uranus because there'll be a fair amount of light in the sky. We'll see Jupiter a lot better right next to Aldebaran, which is the brightest star in Taurus. And if you're really lucky, you'll get the Seven Sisters here, the Pleiades star clusters coming back around. Now, you'll notice we don't see Mercury here. So Mercury at that point has gone either I don't think it's transiting, but it's probably the other side of the sun, which means it's a daytime object. But still, you'll have a chance to do Saturn, Neptune, Mars, Uranus, and Jupiter. Like I said, the only big downside is you've got quite a bright moon there, so taking photographs especially might be difficult. With the unaided eye, without a telescope or binoculars, you're not going to see Neptune or Uranus either. So that's a bit of a pain, but there are 2 opportunities this month to see some really nice alignments. So let's see what exactly is causing that alignment. Well, if it's looking like this, maybe the way to think about it is you're looking at the orbital plane of the galaxy. Now, this is an image I grabbed from NASA, I think. Is it? No, it's National Geographic. So I want to be very careful to give the right credit to the right people here. This is a really nice graphic I saw in National Geographic, and I grabbed from their site. And what you're seeing here is at the center, you're seeing the sun, of course, this big yellow, sort of orangey blob in the middle of pure plasma and energy. Then each of these colored circular lines represents the orbits of the planets. So you can see here the red is the inner orbit of Mercury, orange is Venus, yellow is, of course, the Earth. Mars here is this sort of faint green line. You then naturally have the asteroid belt. Jupiter is the green line. This sort of tealish color is Saturn. Uranus is the blue, and the deep violet is Neptune. Now, as you'll notice, they all appear to lie on a plane or a disk. And that is actually how they look in the solar system. If you were to sort of zoom right out and be in a spacecraft and look in at the solar system, you would see the planets all more or less in a line. Now you've got something funky going on here. You've got a comet orbiting the sun. Now comets in the Kuiper belt, which is a cloud of comets and asteroids just outside of the orbit of Pluto. Well, it actually goes from Neptune to somewhat outside the orbit of Pluto. The Kuiper belt is also in that flat plane, which we call the ecliptic plane. So the ecliptic plane formally is the line that defines the midpoint between the Earth's orbit and the sun. And so what the ecliptic plane goes all the way out to most of the planets. If that's the sun, most of the planets lie on that ecliptic plane. Now, the comets and the asteroids in the Kuiper belt also mostly, not completely, but mostly lie in that plane as well. But as you go farther out, even more, and this can go way outside the solar system. You can have several diameters of solar systems out from the sun. You encounter what's called the Oort cloud. Now, the Oort cloud are comets and asteroids that are all over the sky. So they're basically a sphere all around the solar system. So they can have orbits clearly that don't lie in a plane. And here's a good example of a non-planar comet here. It's got this funky orbit that, of course, orbits the sun, but it's not along the ecliptic plane. It's at some vast angle compared to the plane. Now, how do I know all these planets, the major solar system planets in the asteroid belt, how do I know they lie in a plane? Well, we've got this great data table from NASA, and these are fundamental parameters of all the major planetary objects and the Earth's moon in the solar system. Now, there's an awful lot of information here. So, there's mass and gravity and escape velocities and so on. But the one we really want is this one, orbital inclination. Now, Earth here, by formal definition, is 0. The ecliptic plane is defined, as I said, from the Earth's orbit, the center of the Earth's orbit to the sun. That's a very formal definition. That's the 0-degree plane. Well, you can see that Mercury is about 7 degrees off that plane, which means it's not quite flat. It's just a little bit tilted. Venus is similar to us. It's right on the plane, about 3.5 degrees. The moon is 5 degrees off the ecliptic plane. So if that's the ecliptic plane, the moon actually angles at about, orbits at about a 5-degree angle. Now that naturally explains very well, by the way, why we don't get eclipses every month. Because of course it depends where the moon is in that 5-degree orbit, that tilt. To get an eclipse, the position of the moon has to be right on the ecliptic plane, so it's directly in between the sun and the moon. Sorry, the sun and the Earth. Okay, Mars is doing pretty decently, a degree or so. Jupiter the same, Saturn the same, Uranus and Neptune a couple of degrees. Now here's the biggie, Pluto, 17.2 degrees. So if that's the ecliptic plane, Pluto's quite angled actually. And that is one of the reasons why at the International Astronomical Union meeting about 20 odd years ago now, that's why one of the reasons why Pluto was demoted from being a planet to a dwarf planet, or a dwarf planet, is because it doesn't lie along the ecliptic plane. So that's a really nice mathematical way of thinking about it. But as humans, we don't jumbling all those numbers around in our head is not an easy way to think. So let's have a think about how solar systems, suns, are formed. Now, here's this really sort of simple graphic from an old colleague of mine at the European Space Agency, Mark McCrocken. I used to work in a couple of collaborations with him. Really well-established scientist that looks at very young star-forming regions, similar to Orion in the green screen behind me here. And Mark put together this really nice cartoon of essentially how stars are born. Sorry, quick slurp of tea there. You know, the British and their tea. Right. So you get this cloud collapse. Basically, you get this big blob of gas, some dust, of course, and under gravity, it sort of wants to collapse. Now, normally it needs a reason, because if it's just sort of sitting there stably in space, it doesn't really collapse that easily. But if there's a nearby supernova that sends a shockwave through the cloud, or a passing star, or a giant molecular cloud like Orion, that can actually trigger star formation. And by triggering star formation, what that means is the cloud of gas starts to collapse in on itself, which is what you're seeing here in the very top left. That's the first graphic. Now, as that material condenses, starts to collapse in on itself, it starts spinning, and it spins because of conservation of angular momentum. There's no way it can stay not spinning. And so what you get is you get this centrifugal driving, essentially, of them. Instead of the material being a blob, it gets squished down into like a pancake. So you get this central star, and I'm pointing at the screen, you can't see me pointing. You get the central star in the middle. You get this disk where material continues to infall and accretes material onto the central star. And then you tend to have these molecular outflows or gaseous outflows. And we think what that is, it's the way that the star is allowed to get rid of angular momentum. Because if not, it just spins too quickly and the whole thing breaks apart. So we think these outflows of gas at the sort of rotational poles is a way of getting rid of excess angular momentum so that the star doesn't spin too quickly and destroy itself. Well, as you might imagine, in that thick disk around the star, right, you've got your central star, and then there's a thick disk of material. You can imagine then that perhaps some objects might start forming themselves, and that's exactly what we think how planetary formation occurs. And you can see that in this bottom left graphic, and I'll show you in a bit more detail in a second. You start to get these sort of mini gravitational collapses around sort of seedlings of cores of planets. And then so you start getting gaps in the disk where a protoplanet, an early planet, is starting to sweep up material as it orbits the central star. Now, of course, it sweeps up material as much as it can. But once the central star's engine turns on, it achieves nuclear fusion. What ends up happening is you get this big surge of radiation pressure from the central star, and it tends to blow away any materials that haven't already accreted onto planets, which is one of the reasons why you don't get, it limits the size of planets. And so a mature solar system here, going from collapse into a spinning accretion disk, into planetary formation, and then a mature system, and that would have taken maybe of the order 8, 10, 12 million years, that kind of number in our solar system. Many solar type stars take about 10 million years for this process. You end up then having a central star with a planetary system orbiting it. And the fact it's on the stars that the planets are in a plane is a natural consequence of this spinning disk that was produced by the original collapse of the gas cloud that produced the star. So you can see that the planets really should lie along the same plane because they come from the same accretion disk. So that's a really nice explanation. Well, here's a great little cartoon I found of the whole process from on NASA's educational site. It's a really nice graphic that their education folks have put together. And if we start here at the top left, this is sort of a cartoon version of what I just said, basically. So for Earth, for the solar system, about 4.5 billion years ago, more or less, we got the collapse of a big gas cloud. Now, almost always stars don't form on their own. They tend to be part of big, giant molecular clouds, similar to the Orion Nebula of the image behind me here that I'll talk about in a second. And so you tend to get pockets of star formation, which is why star clusters tend to be made up of thousands of stars, or in the case of not giant molecular clouds, globular clusters, there can be hundreds of thousands to millions of stars. So it's very exciting. Now, as we discussed, at some point you start to get inward collapse of this gas cloud, again, possibly from a passing supernova, possibly from a passing giant molecular cloud or a really massive star. And once that collapse occurs, that material crunches down, starts forming this flat disk of dust and gas, and then around the central star, you get accretion onto the material. It's not a star yet, don't forget, it's just a hot central blob. Now, at some point, the temperature and densities become hot enough that hydrogen, you probably can't see the graphic here very well, but you get 4 protons, basically, 4 hydrogen atoms minus their electron, fuse, a nuclear fuse, that releases then a lot of energy, and it turns those 4 protons into a helium nucleus. So 2 protons, 2 neutrons. Now, of course, that massive release of energy eventually becomes a chain reaction, and then the sort of star turns on. It becomes a real star, not just a big blob of hot gas that's becoming more and more dense. Well, again, because it's spinning so quickly, it ends up forming this sort of pancake disk, and you can see that right in the middle here. And so what ends up happening is now you've got a lot of material that can become a bit blobby, a bit condensed, and around a seed of what is going to become a planet, you get then accretion onto that planet. So Jupiter at some point probably started out as a small asteroid, a small lump of rock that started up under gravity, started attracting gas and dust onto it, and became bigger and bigger and bigger, and eventually became the Jupiter that we know today. Now, that's also true, of course, for Earth. Earth started out as probably a blob of rock, started collecting a whole bunch of heavy elements such as nickel and iron and silicon and oxygen and thankfully carbon, and became the terrestrial planet that we know today. Now, of course, you do get a range of planets. The heavy, rocky terrestrial planets are the inner planets. And by inner, we mean inside of the asteroid belt. So Mercury, Venus, Earth, and Mars. They're all very, very rocky. They have dense metals at their core, so typically iron and nickel. Now, they have some light gases, such as oxygen, hydrogen, helium, those kind of gases. But most of those gases boiled off, or they weren't able to gravitationally accrete onto the planetesimal, the sort of like protoplanet, because they were too hot. They had too much energy. They couldn't overcome the attractive force of gravity. But farther away from the sun, the outer planets, outside of the asteroid belt, temperatures were much lower, and so those gases were moving much slower. And so planets such as the giant planets such as Jupiter, Saturn, Uranus, and Neptune, they were able to accrete on a lot more of the gases, the hydrogens, the heliums, a little bit of carbon, so you can get the methanes of this world. Throw in a bit of nitrogen, you can get the ammonias of this world. But they became mostly gaseous, because once they started becoming bigger and bigger and their force of gravity grew as their mass grew, they were able to sweep up vast amounts of gas in their orbit, and they became the giant planets. And again, so you finally end up with a sort of present day sun where, again, the planets are in a line because they were formed in a flat accretion disk. Now, it's not completely flat, right? I mean, there's a little bit of width to it. I mean, I don't know the actual number, but it could be, I don't know, it could be 1,000,000 miles thick or something like this. Now, that would naturally explain why some of the planets don't lie on the exact same orbital plane as the Earth. Yeah, I mean, there's also encounters, right, with asteroids or comets that come into the inner solar system. So that might explain a little bit of deviancy away from that as well. So that's a really nice cartoon graphic of how the whole process starts. Now, as we talked about, and I've got the image up behind me here, this is a picture I created of the Orion Nebula, a very small part of the Orion Nebula, I should say, way back. This is probably 15, maybe 20 years ago now. I made it using the 0.9 meter telescope in Ceratololo near La Serena in Chile. And what I did was I took about 900 seconds worth of exposure in 5 different filters. So in the Cron-Cousins system, it would be the Johnson's Cron, the Johnson-Cron-Cousins. The Johnson filters were the UBV, the Cron filter was the R, and the Cousins filter was the I. And about, like I said, 900 seconds-ish in each. Maybe a little bit longer in the U and B because the detector doesn't have a great response in U and B. Now, each of these people, Johnson, Cron, and Cousins, they were people, they were astronomers. And what they did was they came up with very specific filter systems, colored filters that you stuck in front of your telescope, or actually behind the objective mirror, so that you could measure the different brightnesses and temperatures of stars, or brightnesses of stars in different filters, different wave bands. And when you combine them, you were able to do things like measure their temperatures. And that's really important. Now, Alan Cousins was a particularly interesting man. I met him several times in the South African Astronomical Observatory in Cape Town, and he was a sort of living legend when I met him. He was in his 90s, and every day we would go for tea at the library at the observatory there in Cape Town. And I used to observe a lot in those days in South Africa. And tea would be at 11, and we would have tea and biscuits, and you talk to all the astronomers and the grad students and the support staff and the technicians and so on. And it was very nice. It was very sort of convivial, and you got to know everyone, and it was just very pleasant. Well, Alan Cousins would talk your socks off. Now, remember, he's a fairly old guy at this point, but he had a lifetime of stories. And he started off as an electrical engineer, could fix anything, basically. And he got very interested in photometry. And until his dying day, he was still measuring the brightnesses and the accuracies of his standard stars, his photometric stars that he measured with these filters that he came up with himself, the eye filter specifically. But when he was a very funny guy. So when you were talking to him, I mean, he was 90, right? And he had false teeth. And when you were talking to him, sometimes he was so excited about the astronomy. And sometimes he would observe the night before at 90 years old, and he'd be at the telescopes. And the next morning, he'd be telling you at tea about these sort of millimag differences in his standard stars. But he would talk so rapidly, his teeth would fall out. And so he'd be telling you about this sort of one of the exposures, and then he'd go, and his teeth would fall out. But even at 90, he had amazing reflexes. He would catch his teeth, pop them back in, and just carried on talking about his photometric system as if nothing had happened. Well, as a young man, I couldn't always control myself, and I would be giggling like a little 6-year-old girl. Oh my God. He was a very, very funny man, but incredibly knowledgeable, and taught me an awful lot about how to use photometry to measure the brightnesses and temperatures of stars. A wonderful, wonderful scientist. Anyway, sorry, I sort of digressed to one of my old stories there. But so yeah, this Orion is obviously a very good site of star formation that we know about. And of course, each of these colors here represents a different gas. The red is hydrogen gas, and it's glowing away in the red because it's been excited by possibly a bright star like this one here on the left. And all these gases are not yet forming stars, but all of these bright looking objects that are indeed young stars, they've just formed actually. The Orion Nebula is about 1 to 2 million years old for the most part. There's a little bit of age variation across the image, across the nebula, but not too much. It's definitely a couple of million years plus or minus 1. A very, very young group of stars there. So this is some of these stars here. They may be young enough. We can't tell with our eyes; they're too far away. We have special kind of measurements that we can tell. And some of these stars may well indeed have young accretion disks, and so there could be sites of ongoing planetary formation right now, this very day. And so that's really interesting. So Orion's a really beautiful place to look for these things. Now, I know you didn't take my word for it necessarily. I mean, hopefully I know my astronomy well enough that I know it's true. But here is some, so again from NASA, some Hubble Space Telescope images. This is the WIFPIC camera, the Wide Field Planetary Camera 2, which means it was the upgraded version, taken in 1995, again, with an effort led by Mark McCrochen, my old colleague, and Chris O'Dell, who I used to work with in Vanderbilt University, actually. And these are images that they had the Hubble Space Telescope take of protoplanetary disks in the Orion Nebula. So now, I don't think there are any of these stars here that we're looking at in the background of my green screen image, But some of these stars are in Orion. So these are 1-2 million years old, maybe, and these are direct images. Okay, so these are these look like to be this probably optical, maybe optical red. Actually, can't be that red because if they were in the infrared, we would be able to see through the disk a bit better. But what you're looking at in each of the 4 panels is there is a central bright object that is a young star in the middle of forming. They may, in all cases, it looks as though the central engine has turned on. It's nuclear fusion has started. That tends to happen pretty quickly. That normally happens within the first 100,000 years, 500,000 years-ish of forming. So these are probably old enough, given they're 1 to 2 million years old. So the nuclear fusion will have started. But you can see there is a black disk around all 4 in the stars in those panels. So we think these are the protoplanetary disks of star formation. Now, these are great sites for potential planets being formed in these disks right now. Orion's not so far away that, this occurred millions and millions of years ago. I can't remember the exact distance of Orion. It's a couple of hundred parsecs, I think. So, it's the ongoing planetary formation is occurring. So these would be really good candidates in 10 million years if we could survive that long to be able to go back and follow up and say, are the planets there? Because we saw the protoplanetary disk. These objects have got a great chance of hosting planets. And here's some others. These are from 6 objects in Taurus. Are they all in Taurus? Koku Tau is, DG Tau, yep, Harrow, I think that one is. Yeah, judging by their right ascension declination, I think they are. So I can tell here by the first 5 numbers here are a right ascension, which is basically a longitude. And then the last 4 numbers after the plus sign, that's a declination, which is similar to latitude. That puts it in Taurus, I think. This is north of Orion. Yes, these are all in Taurus. Now, again, Taurus is a very young star forming region, a couple of million years old. Now, this was taken by the NICMOS camera. Now, this is an infrared camera, so the infrared is good because it allows you to peer through some of the dust that obscures some of these central objects. Now, these are beautiful because what you're seeing here, the Koku Tau is a difficult one to judge. But as you go to DG Tau and the Harrow 65b, what you're seeing here, there is a central star, but with the black line, you are seeing the shadowed, silhouetted accretion disk. Again, you can't, the plus 2610 one is difficult. You can see the disk of plus 2616. It's looking a bit like this. And then this bottom right example, this plus 2247, beautiful, beautiful example there of an accretion disk around a young stellar object. So this is just beautiful edge-on silhouetted accretion disks around these very, very young stars. And it explains very, very nicely why planets end up in alignment around in a solar system and other stars probably because the stars were all formed from an accretion disk that is coplanar. That is, it looks like a flat surface, more or less flat, of course. So let's just go back to the original image. So this is what we can expect to see tomorrow morning. Hopefully, like I said, if you're no trees in the way, there's no early morning haze, and you're able to see Jupiter and Mercury are going to be really tough. That looks to me as though they're going to be fine, well, maybe a bit more, 10 degrees above the horizon. That's going to be tough because even in the sort of pre-dawn, the scattered light from the sun is quite substantial. You'll see the beautiful crescent moon, very, very thin crescent, which is beautiful in and of itself. You should be able to see Earthshine on the dark side of the moon as well. But an Earthshine is when you're seeing scattered light from Earth's atmosphere then reflect off the dark side of the moon. And so even though you see a thin crescent, this part of the moon is not completely dark. You actually see a little bit of detail. Comes out really well in a photo. Mars, super easy to see, of course, the beautiful red planet, and Saturn's pretty bright. The rings, I did check this yesterday, the rings are pretty open right now, so they're tilted. Sometimes if you're really unlucky, and it of course depends on the orbit of the Earth and Saturn, sometimes the rings are in a line, so you don't really see much. But I think right now they're quite tilted. I think, is it 17 degrees? I can't remember the number, but you'll definitely, through a small telescope, you've got a great chance of seeing the tilted ring system. So get out there tomorrow morning and give it a go. I don't know, you've got a better chance. Well, I don't know how much of this you'll see from the southern hemisphere. You'll probably definitely see all this. All of these are in the ecliptic plane, and you can see that from the southern hemisphere. But from the northern hemisphere, this is what you'll see, certainly from mid-latitudes in North America. Yeah, go out there, have fun. And if you don't really manage to see it tomorrow morning, you've got another chance on the 30th of June, about 1 hour before sunset. So a little bit less pre-dawn haze, right? It hasn't quite gone into twilight yet. But of course, we lose Mercury, and the moon is much more illuminated. It's in the last quarter, so it's about a half moon. So it will make seeing the other planets difficult, Uranus and Neptune especially, even taking a photograph with a decent camera. Anyway, good luck. That's our episode for today, and thanks for watching. Thanks for joining us. Well, this wraps up another presentation for Astraveo, where we go from geek to chic by sharing our passion and excitement for all things scientific, especially astronomy and in the mysteries of the universe. If you enjoyed this video, please hit the like button, and in the comments below, please leave us your suggestions for future presentations. We'll get right on it. And don't forget, you can join us on our journey by subscribing and hitting that bell. He's Joseph, and I'm David, and together we're Astraveo. Thanks for watching.